Am I real or am I imaginary? At least I know I'm complex. Anyways, today I'll be teaching you about the least complex part of Math 2, complex numbers. To begin, we'll examine the complex number system. Okay, back to this. The complex number system, it's kind of simple. There's two situations. Either a number is complex, or it is not.
That was easy.
So we're going to start from the bottom and work our way up. At the bottom is the set of natural numbers. And the set of natural numbers is the numbers 1, 2, 3, so on, so on. Basically, it's all of the positive numbers greater than 0. All the positive whole numbers greater than 0. Above this is the set of whole numbers. And the set of whole numbers is equal to the set of natural numbers plus 0. It's a very useful category. Use it all the time. Helps you with the CPCTC all the time. Easy. Above the whole numbers is integers. Now, integers, they're pretty good. They are basically the set of whole numbers and its opposites. So it includes 0, 1, 2, 3, 4, and it also includes numbers like -1, -2, -3, so on, so on, so on. But they still have to be whole negative numbers. Above integers lies rational numbers. And rational numbers are all of the numbers that can be written in the form a over b, where both a and b are integers. So, for example, it includes all of the integers, and it also includes fractions like 2 over 7, 3 over 4. To the side of rational numbers lie irrational numbers. Just as the name implies, are numbers that are not rational. Or another way of saying it is numbers that cannot be expressed as a ratio of integers. So, for example, square root of 2. You cannot express the square root of 2 as a ratio of integers. The only way you could express it would be as the square root of 2 over 1, which is not a ratio of integers because the square root of 2 does not satisfy the condition for an integer. Another common example of an irrational number is pi. Although many of you may be thinking, oh, you can express that as 22 over 7. However, that is just an approximation and that is not actually the value of pi. So, since pi cannot be expressed as a ratio of integers, it is not a rational number. So, as some example problems, would 3 over 4 be considered a rational number or irrational number? If you said irrational, you should rewatch this video, because this is a rational number. Since 3 over 4 is a ratio of integers, it is rational. Next example. Would this expression be considered rational or irrational? Take a second to think about it. The correct answer is rational, because the square root of 2 times the square root of 2 is equal to 2! And 2 is an integer, and it's a whole number, and it's a natural number, and you know what that means? Rational. Above rational and irrational numbers is real numbers. Now, you may be thinking, if it's a number, it's real. I mean, I'm real and I think of numbers, so all numbers are real. However, as we'll get to later on, there are also imaginary numbers. So real numbers are all of these, and it just basically everything underneath this is considered to be a real number. As for what I was saying earlier, imaginary numbers, they are over here. And imaginary numbers are numbers which are, just as the name implies, imaginary. Anyways, first let's start off with the imaginary unit. or I. Now, I is not referring to myself. It is actually equal to the square root of -1. And obviously the square root of -1, it doesn't exist because you can't multiply a number by itself and get -1. Alright, so now let's go into imaginary numbers. So to start, we have to explore the imaginary unit, which I assure you I did not just make that up, it kind of sounds stupid. No, the imaginary unit is I. And I is equal to the square root of -1. Now, I see you, Jimmy, I know what you're thinking. Square root of -1 is impossible because you can't multiply and get a number by itself and get the square root of -1. Well, Jimmy, you're right. That's why they're called imaginary numbers. We developed I as a way of representing the square root of -1 so that we could do way more stuff with math. And it's very commonly used. So, since I is equal to the square root of -1, we can use it in many ways. So first, let me show you one usage. Let's say you had the expression the square root of -4. Now, Jimmy, I know it's not possible, we'll get to it. Okay, now, square root of -4, we know that the square root of 4 is equal to 2. I hope. So, in order to figure this out, we're going to say, okay, we have the square root of -4. We are going to factor out, what if we factored out the -1 from the -4? Then that would leave us with -1 times the square root of 4. The square root of -1 times the square root of 4. So now you have 2 times the square root of -1. And as we learned earlier, I is equal to the square root of -1. So this is equal to 2i. Now this is nice because it gives us a way to simplify negative square roots. That's just one usage, however. We'll get into the next in a second. Alright, now we're going to be working with powers of I. So we know that I is equal to the square root of -1. So what would I to the power of 1 be equal to, Samantha? That's right, the square root of -1. Now, what would I to the power of 2 be equal to? Well, that'd be the square root of -1 times the square root of -1. And what's that equal to? I think I heard it. -1. Now, I to the power of 3 is equal to I squared, which is -1, times, times the square root of -1. What's that equal to? It's equal to -1 times I, or the opposite of I. And finally, what's I to the power of 4 equal to? Well, that's equal to -1 times -1. Put that in parentheses for you out there who are freaking out. And what is that equal to? 1. Now, the powers of I go from 1 to 4 goes in a cycle. So, for example, if I were to say I to the power of 5, that would be I to the power of 4 times I to the power of 1. Or it'd be 1 times square root of -1, or just I.
That was easy.
Alright, now, that was easy. To conclude this entire thing, what is above real and imaginary numbers? Well, you might have heard me say it at the beginning. We are looking at the complex number system. Both real and imaginary numbers are complex numbers. And complex numbers are numbers which can be written in the form ax plus bi, where a and b are real numbers, and obviously I would be an imaginary number. So, So, for example, let's say we have the number 3x plus 4i. This number is not real because it has an imaginary part, and this number is not imaginary because it has a real part. So it would be considered a complex number. Now, as you can see, each number inherits the traits of whatever is beneath it. So a complex number could be both a real number could be considered a complex number, and an imaginary number could also be considered a complex number. This is true because let's say we're looking at a natural number like 3, okay? How could we write 3 as in the form ax plus bi? Well, you could say something like 3, where x is 1, plus 0 times I, which is equal to 3 plus 0, which is equal to 3. Hard math right there.
That was easy.
And let's say we wanted to say an imaginary number was complex. You could say 0 times x plus, I don't know, maybe like 4i. And this is equal to 0 plus 4i, which is equal to 4i, which of course we know is equal to the square root of -16, which is why it is is considered imaginary and complex. For now, we went over the complex number system and the imaginary unit, a little introduction to it, some simple operations with it, but we'll go more in depth into it in a later video. Matthew Lacayo signing off.